Alright, conic section number 3 here, excuse me, I'm going to cover that up, is an ellipse. So an ellipse is our third conic section. Let's take a look at how our plane would intersect our conic for an ellipse. Here's our conic, pretty crude drawing. If I have a plane that comes through and intersects my cone, but doesn't intersect in a way that's parallel to my base or perpendicular to my axis, I get what's called an ellipse, and it's kind of an elongated circle. So how does that work as far as a graph? Well, my ellipse might look, pretty rough drawing, might look something kind of like that. Okay, so let's go to the definition of an ellipse. So first thing we need is we need two unique points in a plane. So I'm going to come here, let's get a new sheet. I've got a point F1 and I've got F2. Okay, F1 and F2. Now what happens is I'm going to take all the points that I take and I have the same sum of my distances to those 2 points. Okay, I'll come back to this, but I want to show you on a drawing. So let's say this isn't a point on my ellipse. Let's just call it x comma y. Keep it generic because we're pretty good at doing that here lately with these conics. Okay, so from F1 to my point, let's call that D1 for distance 1. Okay, now let's come over here and let's go from F2 to my point. Let's call that D2. So what happens is the ellipse is the set of points that these two distances, the distance to my first F1 and the distance to F2, if I add those two distances up, it's always constant. D1 plus D2 equals K. Let's not call it K. We've used K too much here lately. Let's call it Q, just for something different. And it's just some constant. It's the sum of the distances. So let's go back here and let's make sure that all makes sense with our definition. Collection of points in which the sum of the distance from F1, the distance from F1 was D1, and the distance from F2, that was D2, is constant. The sum is constant. Perfect. So give me a little bit more of a drawing here, no matter where I move around this. Maybe I'm over here. This would be now D1, and this would be now D2. And I keep following that pattern all the way around, and what I should end up with is my ellipse. I'm going to show you a video, and let's thank Mezon.biz for this YouTube video that they've got. Now there's not any sound with this, so I might pause and kind of talk about it as we go. But here we go. So they're going to draw a perfect ellipse. So what do you see here? You've got 2 points. And these are those 2 points that we were talking about. Right here we've got point F1. That's not what I meant to do. Apologize. Right here we've got our toothpick on the left. That's going to be F1. We've got our toothpick on our right. That's F2. So we've got our 2 fixed points in a plane. Now they're going to put this string around these 2. And what happens when they pull it tight, well, that string's looped, so it never gets any shorter or longer. The loop's always the same. So when they pull it tight here, what you end up with is this line over here is D1. We'd have a similar line over here, which would be D2. Because the loop never changes size, the length between the toothpicks never changes distance. So the sum from my right side and my left side should stay the same. So let's play that and let's see what happens. Now those lengths change, but the sum of those lengths always stays the same. So right here, here's another look. Here's D1. Here's D2. If I were to measure those lengths and add them up, they would be the same right here if I took D1 plus D2. And we have an ellipse.